Welcome to this deep dive. Today we're jumping into modular arithmetic, which is this really elegant system where numbers sort of wrap around, like the hours on a clock, right?
Exactly like a clock. It's a concept Gauss really laid out formally way back in 1801 in Disquisitioni's Arithmeticae. Hugely influential work.
Absolutely. And we're going to focus on something specific within that today, something called adjacent residues.
That's right. And this connects, interestingly enough, to the online encyclopedia of integer sequences, the OEIS, specifically sequence A000236. For number theory students tuning in, the OEIS is just an indispensable tool.
Oh, definitely. Okay, so before we get lost in the sequences, maybe we should pin down the basics, like congruence modulo M.
Good idea. So A is congruent to B modulo M. Well, it just means A and B have the same remainder when you divide them by M.
Right.
Or you could say M divides their difference, M minus B.
Okay, like 38 and 14, modulo 12. They both leave a remainder of 2.
Exactly. So 38 is congruent to 14 mod 12. Perfect.
Got it. And building on that, quadratic residues.
Yes. So for a given modulus, let's say n, an integer q is a quadratic residue if it's like a square in that system.
As a square.
Meaning there's some integer x where x squared is congruent to q modulo n.
Oh, okay.
And if you can't find such an x, then q is a quadratic non-residue. Simple as that, really. Some numbers act like squares, others don't.
Right. Okay, so adjacent residues, this is where we look at numbers next to each other.
Precisely. We take a prime number, p, and look at the integers, say, from 1 up to p minus 1, and we ask, if we pick a number k, is it a quadratic residue or non-residue? And what about the next number, k plus 1?
So like if k is a square mod p, is k plus 1 also a square? Or maybe it's not.
That's the question. And we use the Legendre symbol to classify these. It's just notation kp, which is 1 if k is a residue, and any 1 if it's a non-residue. Helps keep track.
Okay, and we're looking at k from 1 up to p minus 2, right? Because we need k plus 1 to still be less than p.
Exactly.
Right.
We define 4 sets based on these pairs, k plus 1.
What are these sets? Lay them out for us.
Okay, so first, A0. This is the set of all k, where both k and k plus 1 are quadratic residues. So kp equals 1 and k plus 1p equals 1.
Residue followed by residue. Got it.
Then A0, that's where k is a residue, but k plus 1 is a non-residue. So kp1, k plus 1p equals 1.
Residue, non-residue. Okay.
Next, A0. The other way around, k is a non-residue, k plus 1 is a residue, kp high 1, k plus 1p equals 1.
Non-residue, residue. Makes sense.
And finally, air. That's when both k and k plus 1 are non-residues. Kp minus 1, k plus 1p minus 1.
Non-residue, non-residue. So these 4 sets cover all the possibilities for consecutive pairs.
They do, and the fascinating part is counting how many elements fall into each set. We call these counts alpha ij, so a arrow, I arrow, arrow.
And is there a pattern to these counts? Or is it just random depending on the prime p?
Oh, there's definitely a pattern, a really quite beautiful one. It depends crucially on whether the prime p is congruent to 1 or 3 modulo 4.
Ah, okay. That distinction comes up a lot in number theory.
It really does. So we actually have formulas for these counts, the I eval value.
Formulas. Let's hear them. This is where it gets interesting.
Okay. If your prime p is congruent to 1 modulo 4, so it's like 5, 13, 17, etc.
Right. Form 4n plus 1.
Then the number of residue pairs is p5, 4.
Okay.
And the other 3 counts. Residue, non-residue, non-residue, residue, or non-residue, non-residue. They're all
equal. To what?
They're all p1, 4.
Huh. So 1 is different. The other 3 are the same when p is 1 mod 4.
Precisely. But now, if p is congruent to 3 modulo 4, so primes like 3, 7, 11, 19.
Form 4n plus 3.
Yes. The formulas shift a bit. Now, it's the residue, non-residue count. IS, that's different. It becomes p plus 1, 4.
P plus 1, 4 this time. Okay.
And the other 3, I, air, and IS, they're the ones that are equal now.
And they are equal too.
They become p3, 4.
Wow. Okay, that's remarkably specific. The counts depend entirely on p mod 4.
It is quite striking. It shows there's this underlying structure governing the distribution. It's not just haphazard.
Can we make this more concrete? Maybe walk through an example.
Absolutely. Let's take p equals 17. Now, 17 is 1 mod 4, right? 4 times 4 plus 1.
Right. So we use the first set of formulas. Expect 17 to 5, 4, 4 equals 3. And the others to be 17 to 1, 4 equals 4.
Exactly. So first, you list the quadratic residues mod 17. They are 1, 2, 4, 8, 9, 13, 15, 16.
Okay.
Now we look for adjacent pairs. Residue A0, 1, 2 is RR, 8, 9 is RR, 15, 16 is RR.
That's 3 pairs. 1, 8, 15. So A0, 3 matches.
Perfect. Residue, non-residue A's, 2, 3 is Rn, 4, 5 is Rn, 9, 10 is Rn, 13, 14 is Rn.
4 pairs. 2, 4, 9, 13. Also matches.
Yep. Non-residue, residue, 3, 4 is Nr, 7, 8 is Nr, 12, 13 is Nr, 14, 15 is Nr.
4 again. 3, 7, 12, 14.
Also.
Check.
And finally, non-residue is AO, 5, 6 is NN, 6, 7 is NN, 10, 11 is NN, 11, 12 is NN.
Also 4, 5, 6, 10, 11. It works out exactly as the formulas predicted.
It does. It's quite satisfying to see it.
Okay, what about a prime that's 3 mod 4, like 19?
Good choice. 19 is 3 mod 4, so we expect 19 plus 1, 4, 4, 8, 4, 5, and the others to be 19 to 3, 4 equals 4.
Right.
The residues mod 19 are 1, 4, 5, 6, 6, 7, 9, 11, 16, 17.
Okay.
Residue A euros, 4, 5, 6, 6, 7, 16, 17. That's 4 pairs.
4, 5, 6, 16.
Okay.
So matches the formula, 19 to 3, 4.
Residue, non-residue, A euro, 1, 2, 7, 8, 9, 10, 11, 12, 17, 18. That's 5 pairs.
1, 7, 9, 11, 17. Matches. 19 plus 1, 4.
Excellent. Non-residue, residue, 3, 4, 8, 9, 10, 11, 15, 16. 4 pairs.
3, 8, 10, 15. Matches 19 to 3, 4.
And non-residue, A, 12, 13, 13, 14, 15. Also 4 pairs.
12, 13, 14. Matches 19 to 3, 4. Amazing, it holds up perfectly again.
It does. It's a well-established result, but it's still quite elegant to see the calculation work.
It really demonstrates this hidden regularity. Yeah. You wouldn't necessarily guess it just looking at the list of residues.
Not at all. And, Gauss himself was looking into this sort of counting back in 1828.
Oh, really? In what context?
It was related to determining when the congruence x to the power of 4 is congruent to 2 modulo p has solutions by quadratic residues.
Ah, so understanding these adjacent quadratic residue patterns actually help tackle higher degree problems.
Exactly. It's often the case in number theory. Understanding simpler patterns unlocks more complex ones.
Which brings us back, I suppose, to the OEIS. Sequence A000236. What's the connection there? Is the sequence just listing one of these alpha values?
Well, the fact that there is a sequence dedicated to this area in the OEIS is significant in itself. It tells you that these counts, or maybe differences between them, or some other related quantity that varies with the prime p, is mathematically interesting enough to track.
So exploring A000236 might reveal more about these adjacent residue patterns.
Absolutely. It suggests mathematicians have found, or are looking for, deeper properties, connections to other areas, maybe even applications. For anyone studying number theory, digging into that sequence entry could be a really fruitful exercise.
Okay, so let's just quickly recap. We started with modular arithmetic, the clock math. Then we defined quadratic residues, the squares mod n.
Mm-hmm.
And the core idea today was looking at consecutive numbers, k and k plus 1, and seeing if they're residues or non-residues modulo a prime p.
Right, leading to those 4 sets, A, AO, AO.
And the really striking part was the formulas for the sizes of these sets, the alphas, depending only on whether p is 1 or 3 mod 4.
Showing this unexpected regularity in what seems like a random scattering of residues.
It's genuinely fascinating.
It is. It shows that structure can emerge from apparent chaos.
So maybe a final thought for our listeners. We've focused here on adjacent residues, k and k plus 1. What happens if you look at, say, k and k plus 2, or k and k plus c for some constant c?
That's an excellent question. Does a similar structure hold? How do the patterns change?
Or what if you move away from prime moduli? What about composite numbers?
Mm-hmm.
Things get much more complicated then.
Yeah. Oh, considerably more complex. But that complexity might also hide interesting patterns. And perhaps exploring OEIS A000236 further might give you some hints or point towards related research on these very questions.
It definitely feels like just scratching the surface.
It always is with number theory. But this look at adjacent residues, I think, gives a nice taste of the kind of intricate, sometimes surprising beauty you find hidden within numbers. And the OEIS is just a fantastic guide for these kinds of explorations.